The second and third laws of thermodynamics revolve around the idea of entropy. Entropy is the measure of disorder or chaos of a system. Generally speaking, the idea of entropy is pretty easy. You can look at these different phases of matter and see the entropy difference between them. For example, the solid has a very ordered nature. We see all the molecules are kind of stacked up next to each other in a very ordered fashion. That would be an example of lower entropy. Compared to the liquid, where the molecules are free to move around each other, hit each other, bounce off of each other, slip and slide past each other, but they're not fixed. And so that would be higher entropy, more chaotic, more disorder compared to the solid. If you look at the gas, it's even worse. There's gas particles flying everywhere inside this beaker. And they're not just confined to a small space or even any order at all. They are bouncing off the walls. They're consuming the entire space of the container. So the gas is going to be much more chaotic, and it's going to have a much higher entropy than either the liquid or the solid. For this reason, phase changes, such as going from a solid to a liquid, would be considered a positive change in entropy, whereas going from a liquid to a solid would be considered a negative change in entropy. For chemical reactions, we can predict the sign of entropy, or delta S, as the variable is. We can predict the sign of delta S based on just the phases that are involved in the chemical reaction. For the reaction of calcium carbonate and hydrochloric acid, we can look at the phases and determine the sign on delta H. So, for example, if we look at this, we see we have a solid here. We have an aqueous phase for the acid on the reactant side. On the product side, we have an aqueous phase for the calcium chloride. We have a liquid for the water, but we have a gas for the CO2. And so because we know that gases are an increase in entropy when compared to solids and liquids and aqueous solutions, then we could say that while we may not know the value of the entropy for this reaction, we can make a prediction that this is going to have a positive value of delta S. So our delta S is positive for this reaction. The reason for that is because we have a gas over here that is being produced. Gases have a higher entropy than solids and liquids. What if we have a reaction where all the reactants and products are gases, like the one shown here for the synthesis of ammonia? In a case like that, we can actually compare the number of moles of gas on the reactants and the products and use that as a basis for discerning the sign on delta S. So for example, here we have a total of 4 moles of gas. So this is going to be 3 moles of H2 and 1 mole of N2 is a total of 4 moles of gas. On the product side, we have 2 moles of gas. So in this reaction, because we have 4 moles of gas going to 2 moles of gas, we can say that the value of delta S is going to be negative for this reaction. And so that is because we are going from 4 moles of gas, so more moles of gas to fewer moles of gas, is going to be a decrease in entropy. Because as we know, gases are chaotic. They are very high in entropy. So if you're going from more moles to fewer moles, then that would be a negative change in entropy. In the case where we have a reaction that doesn't produce more moles of gas or doesn't produce any moles of gas, then we would expect the change in entropy to be right around 0. So for these two reactions here, we have the combustion of methane, which is going to have basically 3 moles of gas on the left, 2 moles of gas on plus 1 mole, so 3 moles of gas on the right. So the net change here is 0 for the moles of gas. Or in the case of the thermite reaction, where we have solid, solid going to solid and solid, there's no gases involved. And so in these reactions, entropy changes are going to be pretty minimal. We can calculate the value of delta S if we have a chemical reaction and an appendix that has the values for the entropy of various elements and compounds. For the equation we looked at earlier for the formation of ammonia, the equation to calculate the entropy change is going to be the same virtually as it is for the equation to calculate the enthalpy change that we learned earlier in chemistry. So change in enthalpy for the reaction is going to be equal to the sum of the enthalpy changes for the products minus the sum of the enthalpy changes for the reactants. And so what that means is that we are going to calculate this looking at, so we have delta S for the reaction is going to be basically 2 times the S, the entropy, of NH3 minus 3 times the entropy for H2 plus the entropy for N2. So now we have to figure out where we're going to get these values for the entropies of ammonia, hydrogen, and nitrogen. The values that we need for the entropies can be found in the appendix of most any general chemistry textbook. This one that I show here came from the OpenStax textbook. And there's a couple things about this that I want to point out before we go to calculate the change in entropy for this reaction. The first thing that I want to point out is that there are 3 labels here. We have the substance, and then we have these 3 properties. So this one's delta HF, and that's the one that we used back in Chemistry 1 when we looked at the first law of thermodynamics and calculated the enthalpies. Then we have delta G, which is going to be the Gibbs free energy. And then this one is the S, so that's the entropy. And all of these say standard thermodynamic properties for selected substances. And so the standard comes from the fact that these properties were all measured at the same temperature, pressure, and molar concentration. So that is 1 molar concentration, 25 degrees Celsius, and 1 atmosphere of pressure. So that is what this little 0 means here. So if we use these values, we're really calculating the standard enthalpies. And so I'm going to go ahead and put that back into this equation here. So this is going to be the standard enthalpy for this reaction. Now we're going to have to go look these values up in this table. And one thing to note, even though it's not going to be an issue in this particular problem because all of our values are the same, but you can see that the units on entropy are different than the units for the other 2 properties. So this one is joules per Kelvin per mole, whereas enthalpy and the Gibbs free energy have a value of kilojoules per mole. So that could be an issue if we're using the Gibbs equation where we have enthalpy and entropy in the same equation. We have to make sure that we change the units of one so that we have consistent units throughout the equation. So let's look these values up for these substances, ammonia, hydrogen, and nitrogen, and then set this up and solve the problem. So I've looked these values up in the table. You can see here I found the value for H2, and I found N2 here, and then NH3 is down here at the bottom. So I just pulled these images from those tables so that you can see what to look for. So now we're going to go ahead and set this up. We're going to put in the numbers. So we're going to do delta S is going to be equal to 2 times. Now the enthalpy for NH3 is 192.8, and that's joules per mole per Kelvin. And then we're going to multiply that times 2, and then we have 3 times the enthalpy of H2, which is 130 joules per mole per Kelvin. And then we have the enthalpy for N2, which is 191.6 joules per mole per Kelvin. So now we're going to get numbers for these and solve it and get a final answer. So the value we got when we did the arithmetic is negative 198.1 joules per mole per Kelvin. The sign on the number is negative, and we predicted that it would be in a previous example. And the reason why we predicted it would be is because we had 4 moles of a gas that was being condensed down to 2 moles of a gas. And so we predicted that that would be a negative change in entropy. And when we compare the values and actually put the right numbers in, we see that that is in fact the case. The last thing we'll talk about in terms of entropy and calculating entropy is just like with enthalpy. The reverse process is going to have the opposite sign mathematically for the property. So in this case, we can see that this is the one we just calculated. We have a negative sign, negative 198.1 joules per mole per Kelvin. If we reverse this process and we want to go from 2 moles of gas here to 4 moles of gas here, we can just flip the sign on the delta S. And so this one would be positive, and it would have the same value. So this is going to be positive 198.1 joules per mole per Kelvin.